Okay, good afternoon, colleagues and students. Welcome to the first seminar of the PolyU Science Seminar Series in 2022 and 23. We organized this seminar series in order to explore possible collaboration opportunity and nurture interdisciplinary research within PolyU. So we are doing research in order to benefit society. Today, one of the most concern in society is COVID-19. In our faculty, we have a few colleagues who are doing excellent research in this field. So today we invite three speakers from ABCT, AMA, and AP to share their latest research study on COVID-19, mentioned for detection and control. The first speaker is Professor Feng Ye from Department of Applied Physics. He is a highly cited scientist and a well-known researcher in flexible electronics. So today he will talk about highly sensitive COVID-19 sensor with the electrochemical transistor. So without further delay, let's welcome Professor Ye. Please.
Okay, thanks Professor Tsai for the introduction and the invitation. So today I'm very pleased to have this opportunity to introduce our work on using our semiconductor devices for this COVID-19 detections. In my talk, I will give introduction of this COVID-19 antibody detection. And then I will show you our devices that can be used for sensing, that is organic electrochemical transistor. And then I will show you our portable COVID-19 antibody detection platform, our sensitivity and performance. And finally, I will give the conclusion. So you will find that COVID plays a very important role in the past 3 years, and it greatly influenced our GDP and our normal life. So the detection of COVID-19 include the detection of nucleic acid, antibody, and antigen. Well, the most commonly used technique is for this nucleic acid detection based on this PCR and use instruments and big instruments. And another one is for this antigen detection, fast antigen detection. So this is technique is already commercially available, and everyone may have the experience to use it by using this fast antigen detection. Considering the antibody, the difference for the antibody detection, we developed a platform for the biosensors for this COVID-19 antibody sensing, and the purpose is a little bit different. Okay, but for nucleic acid and antigen detection, it can be used. So they can be used for this for the diagnosis of the COVID-19 infections. For antibody detection, it is a little bit different, and it can be used to monitor the past infection cases and the probable effect of this vaccine. And so for antibody detection, it can be used for long-time monitoring and may get some more information that is different from this antigen and the nucleic acid detection. So you will find for this antibody detection, we will be able to detect the past infection and the clinical care assessment. Vaccine is also very useful for vaccine development, and it is also useful for this epidemiological study. So for this antibody detection, the commonly used techniques based on this ELISA, based on the antigen-antibody reaction and enzyme labeling, and use optical method. But this is large equipment, and it is not very convenient. It will normally take 1 or 2 days to get a result. And we also can find the fast antibody detection kit from the market, like this LFIR. It's also based on this antibody-antigen reaction and nanoparticle labeling and color change in certain region can indicate the antibody. But the sensitivity is very low, and we cannot get the accurate value or accurate concentration of the antibody from this test. So in our experiment, we try to use highly sensitive biosensors, that is organic electrochemical transistor, OECT, for this antibody detection. And we have studied this type of devices for more than 10 years and have been successfully used for the detection of protein, glucose, cells, and DNA, bacteria, etc. So this type of OECT-based biosensor is highly sensitive, and it can be easily operated. It is a low voltage device, so the operational voltage is normally less than 1 volt. For this of OECT, you will find it is a type of transistor. So some people ask me about a device. I always mention that it is a transistor, but it is different from a conventional transistor we normally use in microelectronic devices. We call it the electrochemical transistor. Okay, for conventional transistors, we have the gate dielectric and gate, so we have the field effect. But for this electrolyte gate transistor, we don't have the dielectric. We have the electrolyte instead of the gate and metal gate and dielectric. And actually, it is electrolyte gated. So the electrolyte is used as a gate. And if we apply a voltage, the ions may diffuse into the organic semiconductor layer, and then can induce electrochemical doping in the organic semiconductor layer. So this type of process is also reversible and can get a high tunability of the connectivity of the organic semiconductor layer. So we can get the similar performance to a typical transistor. And this type of device is very sensitive to the voltage, and the working voltage is very low. So in this case, if we have a very small change of the voltage on the applied voltage of the transistor, we will get a response, a very big current response. This is the reason we can get the high sensitivity of the device. And being different from the typical transistor, we have a figure of merit for this type of OECT. If we want to use a transistor as a sensor, normally the analyte will induce a voltage change of the transistor, and the voltage change will be converted to the change in the channel current. So for the device, the transconductance, transconductance of the transistor is an important factor in the sensing applications. So it can amplify the signal. So to get the transconductance, GM, this is the transconductance, GM. And then you will find that it is related to the carrier mobility of the organic semiconductor, and it is also related to the capacitance. But this capacitance, we call it bulk capacitance of the organic semiconductor. It is not a capacitance of the, it's not a capacitance of a typical dielectric material, because ions diffuse into the organic channel and induce, it is like a supercapacitor. Okay, so this capacitance is quite high, and for the organic semiconductor material, the mobility is very low. Okay, around 1. Okay? For typical semiconductor materials like silicon, we have 1,500. Okay? For organic semiconductor, we have about 1. But it is enough because we can have very high capacitance, C star. So mu C is a figure of merit for OECT that can influence the transconductance of the transistor. But for mu C star, So this the product of mu and C star is much higher than typical transistor device. The transconductance is much higher. So considering the figure merit of this type of device, you will find there are lots of organic semiconductor materials that have been used in these OECTs. And then you will find the P-dot PSS. This is you can find the number 3. Okay. P-dot PSS is commercially available. It's low cost. So we can use this material for possibly for the commercialization, okay, of these devices. But for this P-dot PSS, okay, here P-dot PSS is number 1, and P-dot QS is a little bit different. So it already shows a very high mu C. Okay, the dashed line is mu C. And now the best material is this PG2TTT. But this material is not commercially available. Okay, so actually we can use some commercially available organic semiconductor material to achieve very high performance of the OECTs. So in our group, we developed this sensing platform by using this OECT. So this is a design of our device, and then you can find the device is quite small, only millimeter scale. The channel is less than 1 millimeter, micrometer, tens of micrometer. So it's very small. And then we have source drain and gate, and we can have some different design for different sensing applications. And the device can be inserted into a portable meter, and we can use a mobile phone to get a signal. So it's very convenient. So this type of sensors, not only for the COVID antibody detection, okay, we can enable many different type of sensing applications. This type of device all show very high sensitivity, and we can achieve high selectivity based on the modification of the electrodes. And this type of tests are always rapid, it's portable, and we try to develop non-invasive detection. For example, we detect the body fluid, saliva, sweat, etc. So it's very convenient. So this is the design of a device, and you will find this is a channel region, and we have a gate. One gate with some antibody or antigen can capture the antibody. So IgG is the antibody. So if we modify the gold electrode with spike protein, is antigen. The spike protein can capture this antibody IgG on the surface, and so for sensing process, okay, we already modified the antigen on the surface of the gate, and then we put the sample, the test sample on the surface of the electrode in this region, and we wait for several minutes to get the antibody antigen interaction, and the antibody will be captured on the surface, and then we read the signal. Okay, so it is very convenient. And for the device fabrication, you can find we can fabricate lots of devices in one batch on a piece of plastic. It's flexible, small size, and we can cut it to small pieces, and then we can use it. So you can find the channel region is about 10 to 20 micrometer length. It's very small, and we use photolithography to get the device, and the device shows very stable performance, so we can use it for hundreds of times with very little degradation. And the transistor shows the response speed. But for this device, we can have the response speed of milliseconds. So it's not very fast, but actually the best device can show the response to less than 1 microsecond, but it depends on the design. But for this sensing application, the response time for millisecond is enough, and you can quickly come to the stable state, so you can get a stable channel current response. So for the modification of the data electrode, we actually did we should process the surface modification with several steps. So MAA, immobilizing of this organic molecule MAA, and the EDS, NHS, and the spike protein. And then we should fill this BSA in some spaces. So after we get the antigen, we should fill the spaces without the antigen. And then we use the antigen to capture the antibody, IgG. But IgG is only one type of the antibody. We can also detect other type of antibody. So on the AFM, we can find eventually this IgG can be captured. So you can find the change of the height. So this organic molecule can be captured on the surface of the gold electrode after each step. We can find that after we have the IgG, the height of this small particles actually corresponds to this antibody is bigger. And then we also can categorize surface capacitance by using impedance analyzer. And then you can find after we capture this IgG on the surface, actually we will get the lowest surface capacitance because we have lots of organic material on the surface. So the double layer capacitance on the gate electrode, on the gold electrode is decreased. All of these experiments indicate that the antibody can be captured successfully on the gold electrode. And then we categorize the device performance. So, so the device performance is related to the characterization conditions. For example, the electrolyte we use. At the beginning, we just use the PBS solution with a pH value of 7.2 and 10 millimolar PBS. And then if we test a series of samples with different concentration of antibody, and after the incubation period of time, and then we just wash it, and then we put this 10 millimolar PBS solution on the surface to do the measurement. So actually the transistor cannot be measured in the tested sample. We should test it in a standard solution, so 2 steps, okay? And then you will find if we have a higher concentration of these antibodies, the transfer curve of a transistor will shift to the lower gate voltage, shift to the left. And the detection limit is about 10 to minus 12 molar. It's 1 picomolar. But if the concentration is lower, we cannot get the reliable signal. So the mechanism is due to the change of the surface potential of the electrode. So after we capture this antibody on the surface of the gold electrode, actually this antibody will in a PBS solution, this antibody can have some positive charge. So this positive charge will induce an electric field on the surface. Okay? So it will modulate the surface potential of the electrode. In this case, the voltage we applied on the transistor will be modulated by this electric field, okay, induced by this antibody, and then we can find the change of the device performance. And we also tested the incubation effect of the incubation time. So we find that if the incubation time is too short, we cannot get enough antibody being captured on the surface, so the response is smaller. If we have incubation time of about over 15-20 minutes, we will get a stable signal, okay? Which means the antibody antigen reaction is already stabilized on the surface of the gate after a certain period of time. So at the beginning, we can get the detection limit of, well, actually, if we consider signal to noise ratio, the detection limit is 10 picomolar, and we should take by fitting this curve, we get the time constant of 4.6 minutes. And the maximum shift of the transfer curve of the transistor is 72 millivolts. So it's not very good. And then we try to test the selectivity. We found that the device is selectively sensitive to this COVID-19, this IgG. Okay, for pure PBS solution, BSA, and the human serum IgG, normal IgG, we didn't get a obvious response. Okay, so and for the optimization of the gated of the electrode, we also test the concentration of this spike protein to be modified on the electrode before our test. We find that the optimal condition is up to 10 to minus 7 molar for the spike protein for the immobilization state. Okay, and then we try to improve our device performance by optimizing the characterization conditions. So as I explained before, that you will find the IgG will induce electric field or dipole on the surface of the gate due to the positive charge of this IgG. But this electric field could be screened by the electrolyte. Okay, so if actually the electrolyte may have we have the balance. Okay, which means if the distance is longer than the balance, the electric field will be screened. It will have no effect. So in this case, if we have a lower concentration of PBS solution, like 10 micromolar, the charge on the IgG will not be screened. So it will influence the electric field on the gate directly. So we just check the concentration of the PBS solution from 1 micromolar to 10 millimolar. Okay? And then we'll find that if the concentration of PBS is lower, actually the device response is bigger. Okay, just because of the increase of the balance. Okay, if the balance you can find, if the concentration is less than 100 micromolar, the balance is 7 nanometer. So it's already longer than the size of longer than the distance between the gate and the IgG antibody. So in this case, the charge on the surface of IgG will not be screened by the electrolyte. So we should enable the concentration be less than 100 micromolar. Actually, 10 micromolar, 1 micromolar can give us a very high response. And then you will find for 10 micromolar, we already get almost a saturated response. So 10 micromolar is the concentration we use. And then the device shows detection limit of about 10 to minus 13 here. Molar is 100 femtomolar. And another factor could be the charge of the IgG. So, if we have a macromolecule in the electrolyte, the charge on the surface of this macromolecule is dependent on the pH value of the solution. Okay. Normally for this IgG, the isoelectric point is 8.2. So the pH value, if pH value is 8.2, we will not have the charge on the surface. But if we decrease the pH value of the electrolyte, we have the charge given by this, the potential difference given by this equation, and there are some more positive charge on the surface. So this positive charge will influence the gate electrode. So we just tune the pH value of the electrolyte. If we change but if the pH value is too low, the antibody becomes unstable. So we find that the optimal condition is for this pH value of 5, and then we can get the high response and the detection limit of 1 femtomole detection limit if pH value is 5. And then we test the different type of samples with the antibody. For example, in saliva, we use human saliva and we add the COVID-19 IgG into the saliva. And then with different concentrations, we can get different response. And then you will find the detection limit is about 10 femtomolar reliable signal for the saliva. And serum sample is similar, but in PBS solution, we have the highest sensitivity. That's because PBS solution, well, for the saliva and serum samples, the viscosity is very high. So the diffusion of the antibody is more difficult. Okay? So in this case, we will get relatively lower sensitivity in saliva sample. But 10 femtomolar is already sensitive enough. Okay, much more sensitive than existing fast antibody detection. So another issue is for the the speed. Okay, so how long time it will take for the incubation? Okay, to enable the big response in the device. So we found that here is another electrode. So if you apply a voltage, it has 2 electrodes, where the distance is very small, okay, only a millimeter, less than a millimeter. We apply a pulse, okay, about 1 watt square signal pulse, and if we apply positive voltage, okay, so this electrode, so this electric field will be generated, and this positively charged antibody will be driven to this electrode. Okay, this electrode has lower potential, so in this case we can accelerate the incubation of this antibody on the surface of the gate. So by applying this voltage, we can get a much shorter incubation time, about 2.5 minutes. So in this case, we can get a faster response in the device, both in the PBS solution and in serum and saliva samples. Well, here is PBS. After all of these samples were incubated for about 5 minutes, and we can get an obvious response. But for the samples in PBS solution, we get the biggest response. Okay. And even for 2 minutes incubation period, we can get the obvious response. So this technique can accelerate the incubation. And actually, all of these conditions can be real, like the voltage pulse can be achieved by our meter. Okay, so you will find we have developed this antibody detection with high sensitivity, and the detection limit is about 1 femtomolar in PBS solution and 10 femtomolar in serum and saliva. And we can get a very high selectivity just because of the antigen we use, we modified on the gate. And we can achieve very fast detection. So normally 5 minutes is enough, and it is portable, and it can be non-invasive. So for the future applications, you can find the conventional technique for this antibody detection is based on this large equipment, okay, and the serum analysis. So it is not invasive. Also, it's invasive, not very convenient. And for our technique, we can achieve a very high sensitivity to 10 femtomolar, and can be used for saliva test, portable and rapid test. It's non-invasive, and all of the test process is very convenient. We only need a very little amount of the liquid, okay, microliter. One microliter liquid is enough because our device is very small, and we just cover the area, okay, with a small drop of the liquid. So this type of devices can be convenient to use, and because we can use our mobile phone to control the portable meter by Bluetooth. So actually, we can store the data, okay, in our mobile phone, and we can monitor the antibody levels, okay, for a long period of time for some different purposes, like for this self-healing diagnosis, for doctor requirement, or some government assessment of this epidemic risk assessment, etc. And actually, this type of sensing platform, it can be used not only for this COVID antibody detection. We can use it for many different type of antibody detections, okay, for different diseases. So it's very convenient. So finally, I would like to acknowledge my students. Actually, my PhD student Liu Hong finished the majority of the work, and Song Jiajun, he is now is a postdoc in my group, and Liu Chunqi, Zhao Zheyu, Yang Annan, and Wang Meixiang. They are all my students and worked on this project. And we also need to acknowledge our collaborator, Professor Helen Law from HTI. So she helped us to collect some samples. So you can find here. So here is Liu Hong. And this work was supported by the RGC project and some internal project, internal funding. Okay, thanks for your attention.
Okay, thank you very much, Professor Ye. So I know audience must have some questions, but we will keep the Q&A session in the end of this seminar. So let's take Professor Ye again. Next, we will invite our second speaker in this seminar, Dr. Amber Zhao from Department of Dr. Zhao is an assistant professor in Department of ABCT. She is also associate director of Research Institute of Food. So today we will talk about the COVID-19 test with the PCR technique. So let's welcome Amber.
So thank you for inviting me for the research seminar. At the beginning, I was scratching my head to think about what should I talk, because the major talk that I will cover today is mainly, I would say, like majority will be like service of the department of the universities. But anyway, I think my talk will cover mostly some common topics that general public may be interested in. All right. So Dr. Feng just showed the same figures as the current cumulative case of the COVID-19 globally up to a few days ago. So currently there are more than 612 millions of the cumulative case and a lot of death. But I believe this number is way underestimation, as there are many hidden numbers not being reported, not to mention few of the countries have never published their data, such as Russia and North Korea. So what is the COVID-19 is the disease caused by the virus, new coronavirus. Now it has a new, more official name, SARS-CoV-2. So it belongs to the coronavirus. It belongs to coronavirus, which the representative structures something like this. Okay, so its genome is single strand linear non-segmented positive strand of the RNA. Unlike the DNA virus, RNA virus mutate quite quickly, so they could undergo some mutations, some drift mutations from time to time, very quickly within months. After 7 years, they may undergo a major shift of the mutation and become a new variant. Okay, so it's rather challenging to develop the RNA virus. The vaccine against the RNA virus. It has been like that in histories. And there are 3 major groups of the coronavirus. They were not the threat for us, for humans, in the human histories, as you know, like we get along with the cold virus. This is one of the typical examples for a very long time. Since we are kids to now, everyone would have colds like maybe a couple times a year. And if we compare the genome sequence, we can see that even for the SARS-CoV-2, it still shares 50% of the sequence, common sequence to the common cold coronavirus. And until a few years ago, there has been some new group of the coronavirus, for instance, the SARS-CoV-2, SARS-CoV in 2003, and MERS. And since then, they start to cause huge either pandemic or some regional infections globally. So where do the coronavirus from? They actually can be found in many different types of the animals. Among all the animals, bat is a huge one. It's a nature reservoir for a lot of viruses, such as Nipah virus, Hendra virus, or even Ebola virus. Those were all from the bat. And in human history, at least for the last 2 decades, we have the new type of the coronavirus, for instance, the SARS in 2002. And after 10 years, we have the MERS. And 3 years ago, we start to have the COVID-19s from the SARS-CoV-2s. And we don't know, and I believe we will have new coronavirus variant in the future. So how does it coronavirus or SARS-CoV-2 infect humans? Here is an assistance to regulate the blood pressures. We call it RAS. Okay, so in this systems, all humans have this, of course. Basically, the angiotensin will be converted all the way to a corticosteroid that can bind to the vessels, and it can lead to the vessel constraint. And in here, there will be an important enzyme called ACE. This enzyme will help the pathway to proceed to the last ones. And ACE2 is another enzyme which acts as a counter enzyme to ACE. It can help to like degrade the angiotensin 1 to angiotensin 2 to another 2 polypeptides. So it works as a counter role as the RAS. And ACE2 is where the SARS-CoV-2 binds. When it binds, it forces the RAS go all the way along to have the final function, the dissemination of vessel constraints, so that it will worsen the injury, particularly the cardiovascular injuries. And where is this ACE2 located? It's present in either the free form in our blood vessels or on the membrane of many cells, particularly endothelial cells in different tissues, in different organs, for instance, lungs or kidneys, intestines. So that since all those organs, those endothelial cells in different organs will secrete and express ACE2, which means when we are infected by the virus, that damage will occur in different type of organs, which is part of the reason why MIC-C occur, the multi-system inflammatory disease. It's because of the presence of the ACE2 on the cells of different organs. Therefore, as not to image why we would have those symptoms, okay? So ACE2 is also highly expressed on lung cells. And since the SARS-CoV-2 is a respiratory virus, so it's the main attack site in our lungs. It has been reported that people have a higher expression of the ACE2 and the lung cells would have more severe outcome after SARS-CoV-2 infections. All right. So current strategy to combat COVID-19, I don't think we need to, like, everyone knows what to do right now, right? So one of the important to prevent or to have the early warning or is the diagnostic. The earlier we know if someone is infected, the sooner we can have this person being treated or quarantined to avoid further transmissions. So currently there are several major type of the rapid test detections. In our previous talk, we have heard a very nice talk about the detection using ELISA, lateral flow device. And in this part, we will mainly talk about the PCR, which is considered as the gold standard to detect the SARS-CoV-2s. The major difference of those two is that in the PCR, we detect the nucleic acid part of the SARS-CoV-2s. We amplify that nucleotide so that the sensitivity will be much lower, because what we detect is an outcome after amplifications. So the LOD could be very low, much lower than the other method, but of course it would take longer times. So in our hand, in our lab, the LOD can reach as low as 1 copy number per microliters. Okay, it's very low. And well, I think about whether I should talk about this, but anyway, the RT-qPCR is the major techniques we use for the nucleic acid, the PCR detection in our lab. For the sampling type, currently there are 3 sampling types: the deep throat saliva, and the second one is combinational nasal and throat swab, and the third one is nasopharyngeal swab. So depending on the purpose of, no, I should say the destination of where you want to go, then we will choose different methods. Currently, PolyU provide the testing using DTS and the CNTS. And okay, anyway, so after we collect the samples, we'll extract the RNA and perform the reverse transcription to cDNA that will being used for proceed to the qPCRs. So during the qPCRs, 40 cycle of the amplification will be conducted. So the result will be similar like this. So when we detect the signal exceeding the threshold, then we will obtain a value of CT. Okay, we call it CT values. You probably have heard of it a lot. So if after 40 cycles there's no CT values, then we consider it as a negative based on the detection site. All right, and the government may have different interpretation about the CT values. For instance, for the CT values over 33 is considered as non-infectious because the viral load may be low. And so we don't comment because we got those inquiry about whether a CT value 30 something is negative or positive. So we can comment on that part because based on the principle of the PCR, that's a positive. Okay, all right, anyway. So currently, the molecular diagnostic lab is the PolyU in-house COVID lab. We received the HOCLAS accreditations in that fulfill the ISO 15189 status under the HOCLAS. And it also entered the list of local COVID-19 RT-PCR testing institute recognized by the Hong Kong government last year. So in PolyU, in the MPLs is under the PolyU, and currently the management is under like 3 departments. We have the lab director from Department of HTIs, while the infrastructure is mainly under ABCTs, and the administrative, the operation is under UCEA. All right, so again, it just shows the overall structures, and we have the top management from 3 different departments. And under the MPL, because it has to fulfill the ISO 15189 under the HOCUS, all the personnel under this lab should have a valid MLT certificate. So our lab director is Dr. Susan Wong from from HTI. And quality manager Mike, who is here on site, and we also have 2 other MLT in the lab, and 1 laboratory assistant. So when did we start this? We started this in the middle of the 3rd wave of COVID-19 in Hong Kong. Initially, it was only a research project, and then after 2 months, after method was set up, we have conducted a routine testing for PolyU External Liaison Hong Kong Sports Institute, who won a very good records in the Tokyo Olympics. And then in the middle of the 4th wave, the PolyU, the MDL, Molecular Diagnostic Lab, was established. And afterwards, we liaised with different departments, including CFSO, ITS, and UHS, to launch a routine testing for the PolyU community who are medically unfit for vaccination due to the policy of campus entrance. You know, like we have to get vaccinated to enter a campus, but not everyone is suitable for COVID vaccinations. And in May last year, we got the ISO accreditation from HOCUS, and the lab was listed as one of the Hong Kong government recognized testing centers, which is also the only university setting. And then in last August, we launched the travel testing service for PolyU communities. And in this year, we set up a sample collection booth for testing service, which is in Podium Y. And afterwards, we entered the 5th wave, and we start to have more and more positive cases on campus. So we conduct the compulsory testing for PolyU Hong Kong Hall, and also we did our social responsibility. We have our contribution to provide a free testing service for the elderly home in March. And then last month, we set up another sample collection booth at Core D to provide the testing service for general public. But this one will be charged service, okay? And the one for the PolyU community will be free. So currently, the testing scope and service of the PolyU include the travel testing and return to Hong Kong, come to Hong Kong, or the practical testing proof, compulsory testings, or people who may have some concerns. Or we also provide the regular COVID-19 screening for senior management in M course. So if you have such need, please check the website under the UCEA. You will see there will be a contact email and phone numbers. So the page here just is a quick summary to see how many cases we have tested. We don't have a positive case here, a number here. Anyway, so as said, the infrastructure of the testing facility is mainly located in under ABCT in WISE. it follows a unidirection workflow, which is a requirement for the HOPUS accreditations. We have 2 collection booths located in D and Core Y. All right, so other than detection, how can we protect ourselves from infections? The many different authorities, including WHO or Hong Kong government or FDA, has provided the guidelines. And among these, vaccination was put as the top one, as we could take the proactive action to stop the transmission from the beginnings. So the reason for the vaccination is actually based on the idea of herd immunities. So herd immunity is not just in theory, right? So it has been showed on the history that herd immunity could be reached if a sufficient number of the populations are vaccinated. So here shows the red dot shows the infected ones, and the yellow shows the vaccination, while the blue shows unvaccinated. Learning from the human history, we have learned that in order to reach herd immunities, a certain population of the vaccination have to be reached. And it also is also related to the R0, which is the infectious capability of the pathogenic microorganism, no matter it's bacteria or virus, right? So the current vaccination coverage in globally has reached to I think between 6 to 70%. The data was obtained in a few days ago. But the vaccination is highly focused on the developing countries, which who have a rich resource to acquire the vaccinations, while for some developing countries who are still under vaccinations. So currently we have more than 100 of different vaccine candidates in the clinical development or in the preclinical. We can see that we have more 172, which is currently under the clinical development, and nearly 200 in the preclinicals. In Hong Kong, we have two vaccine candidates. One is Sinovac. The technique is inactivated SARS-CoV-2 virus cells, and the other one is Pfizer from Pfizer BioNTech. Okay, it's a nanoparticle of the messenger RNA. So lipid nanoparticle. So lipid nanoparticle is used as a carrier or vehicle to protect the messenger RNA, as its positive charge could help the negative charge of the RNA. At the same time, it helps the intracellular delivery of the messenger RNA and help it to escape from the aerosol to cytosol for translation, because the mediators that we have is the messenger RNA, right? So we need to make sure that they can be delivered to a cytosol where the ribosome locates, so that they can translate that message into the proteins, which is the antigen, to trigger the immune response of the host. It has been reported that the lipid nanoparticles has the potency to induce the inflammations or even cytotoxicities, but due to the advantage of many advantage that I just mentioned is used. So under the presumption that the lipid nanoparticle does not induce the inflammatory response, the side effect after injection of the BioNTech is interpreted as the potent effect of the vaccine itself. All right, so currently we have it's another status data to show the vaccination coverage in different countries, and we can see that currently the highest, the most vaccine that has been given to people are Pfizer. Okay, is the first one, and the second one is AstraZeneca. So last part of the vaccination is that currently most of the adults have received the vaccination if they are willing to. However, the vaccination has been further expanded to adolescents, the young kids, the teenagers or the young kids. So currently, there are not many clinical trials being conducted using, on the younger adult. I could only find three. I can only find three that are that have the clinical trial phase 3 done using the Pfizer one, the BioNTech, or the Sinovac. So overall, they show a favorable safety and side effect of the profiles, and there are more clinical trials being conducted, ongoing one, at least 4, for the ages between 3 to 17 using BioNTech and coronavirus. The Sinovac. Of course, there are more other clinical trials of the phase 2 on other vaccine candidates, but since we are in Hong Kong, so I only include the data that are more relevant to us. All right, so other than that, what else could we do? The face mask is probably one of them because, like everyone in this room has wear a face mask. I guess we don't need to explain too much. Why do we have to wear a mask? Mask can efficiently prevent the transmission of the aerosols, where the microorganism could be like hidden in the aerosols and like spray, and then it can prevent the transmission of those. All right. So indoors, we always wear face mask, but outdoors, there has been suggesting for social distancing, where people should not, should sit apart for at least 1.5 meters. So at the end, I would like to acknowledge the PolyU MDL colleagues, and Dr. Cecil Wong is our lab director from HTI, and Mike is our quality manager again, who is sitting there. He's not shy, but but doesn't like to show his face. Anyway, so this is my research lab. We also work on, another important areas of our research lab is gut microbiota. So I hope I would have the chance to share that part of the research next time. Okay, all right, thank you.
Thank you very much, Amber. Thank you very much.
Thank you.
So let's move to the next talk. The last talk in this seminar is by Dr. He Daihai. Dr. He is an associate professor from the Department of Applied Mathematics. Dr. He is an expert in the model on the control COVID-19. He published one paper. This paper can be cited from thousands of times. Dr. is ranked among top 0.1 percentage of authors in the field of disease outbreak worldwide. So without further delay, let's welcome Dr.
Thank you, Professor, and for the invitation, and colleagues for attending this seminar. I'm very honored to have this opportunity. And actually, I just learned from these 2 previous talks. I personally learned a lot. And so my topic is on evaluating the effectiveness of a vaccination campaign globally. And so I will cover those 4 items. So first, I want to summarize a little bit on my work in the very early stage of this pandemic. As we can see, this pandemic already in the past less than 3 years already cost more than 6 million lives, at least that is reported. And this is in the past 100 years, there is nothing happened like this, like in such a short time, like people die every day. And but in a very short time, by one virus, that is very tragic. And so at the very beginning, our team, mainly my student and my colleagues, we working very hard trying to analyze data. So this work, for example, this work is done in February, in January 2020. So we estimated the basic reproductive number. The basic reproductive number is the average number for a typical infectious person will spread to secondary cases in a wholly susceptible population. And so it's very important. So based on publicly available data, we estimate it is at a magnitude between 2 and 3. And most importantly, we emphasize that when we analyze data, we need to understand how this data are collected. And is there any other factors to impact on the data? But we emphasize that we need to clearly understand there is an improvement in the testing. So the data it's not only the intrinsic feature of the virus, but also related to like how frequently you test. So this work is cited by Chinese CDC, and in Google Scholar it's 2000 close to 2000 citing. And second work is it's a possible interference between influenza and COVID-19 among children. If you remember at the very beginning, it was noticed that actually children somehow, it seems they are protected from the virus, not many. So in this work, I found that in one study among people like less than 30 years old, there is a very high influenza positivity. You can see it here, 60% in this group of patients. They are 60% influenza and 0 COVID-19 positivities. Based on this data, I argue that there is possibility at least at the very beginning, there is a possible interference between influenza and COVID-19 among young people or children. This one also I did very early, and I'm very proud of this work. This showed that as a mathematician, we read papers and we try to understand, we try to interpret the data. Okay, so why COVID-19 is so difficult to control? Because it has a highly large susceptible pool. There's not that immunity among population. It has a higher transmissibility, like a basic reproductive number between 2 and 3. Also, there is a important feature is it can transmit among by those asymptomatic cases, right? That is a feature. Like there are some proportion of people, maybe 20%, they are asymptomatic. They have no symptom, but they can transmit the virus. This is one important feature, quite different from influenza. Influenza probably has that feature, but not so frequent. But at the beginning, I found that actually, yes, asymptomatic cases can transmit, but it has a lower relative transmissibility. It's about 1/4 compared to this symptomatic cases. Based on this data, so I published a paper after a year, like 15 months. My colleague from PolyU, they also report that they based on they did a systematic review. They confirmed this number. So I'm quite happy about this. This one, there's another feature as a serial interval. Serial interval is the time a symptom onset of a infector and the symptom onset of an infectee in a transmission chain. That time interval. That time interval at the beginning is around maybe 5 to 6 days. Serial interval, sometimes we call it generation time. The definition is slightly different, but quite similar. And this serial interval we can estimate. So, like a mathematician develop those kind of equations here. So this is using something called a likelihood function. We developed likelihood function. We estimate this parameter. However, this is a contribution of our team because in this pandemic there are strong control measures. Particularly in mainland China, there is a strong control measure. So when you collect data, when you measure, when you try to estimate those parameters, you need to take that into consideration. So basically, we propose a new equation. We take into account the quarantine time. So here in this figure, we showed that if we simulate some data, and if we do not consider the quarantine, we would get a lower estimate. We would underestimate. And if we take into account the quarantine effect, we can get an unbiased estimate. And this one, also this work I did quite early is the serial interval, as I just said. The serial interval, if you observe the serial interval, the reported serial interval, over time, you would notice that it's decreasing. It's decreasing. This is in January 2020. There are some cases. There is a significant trend. It's decreasing, and so we reported this. So the reason behind this decreasing is because of the control measure. So we found a patient, we quarantine it. So it prevent later transmission. So this work after 5 months, and again my collaborators in PolyU, they published a science paper, but they basically reported the same story. So the serial interval decreasing over time due to public health control measures. So I communicated with my friend, Professor Ben Collin, and he emailed me that you have a paper on every issue before us so quick. And PolyU team, it's fair to say that PolyU team is probably like the number one globally on COVID-19. And luckily, we together we got a collaborative research fund. So that is there is another issue actually I did at very early is the air pollution and case fatality rate. Case fatality rate is if you infected and what is the risk you die. It's case fatality rate or case fatality ratio. And we found that in those cities with air pollution, the case fatality rate is high. So my team did quite a lot of small papers because I have a large team. And so actually today I will talking about using maximum likelihood estimation, those techniques to estimate how many lives saved by vaccination campaign, right? So like in Hong Kong, we have millions and millions of vaccines we delivered, and globally in US, like for example, there is billions of vaccine delivered. Of course, it has big impact, it saves a lot of lives. But it also makes sense to can we quantify how the number give an estimate for the number. So we're using maximum likelihood. So I skip detail. Likelihood function is some kind of a probability distribution function of observed data and function of statistical parameters. And a technique I'm using is iterative filtering. So basically, we're using something called sequential Monte Carlo. It also has a name, particle filtering. So basically, we have data, And we define a likelihood function. We try to maximize this likelihood function while we let a parameter to be randomly random walking. So, and we call this process a partially observed macro process. Basically, our data is a time series at some time interval. For example, the daily reported cases, the daily mortality due to COVID-19, and we're using something called plug and play likelihood-based inference. Basically, we divide population into different groups according to their disease status, like a susceptible group and exposed group and infectious group and recover group and vaccination group. And those groups are denoted as xi, right? So xi equal to here xit at some time equal to xi0 at initial value plus some income minus some outcome, and there is a rate. The numbers of individuals in each group changing over time at some rate, so we denote as VIG. They have some rate. They move between groups from one group to the other. So we here see the notation like a VIG means like from one group to the other group, right? Their changing rate is like this, and so they under some condition it's following a Markov process. And this paper is mine. First author published in Journal of Royal Society Interface, and I also cited more than 300. And so, skip the detail. Basically, there is some terminology. For example, we're using multinomial distribution, and yeah, that's the main multinomial distribution. Each time step we for one group, we consider there is a different road individual in this group might go to, right? So there is if there's only one, we can use in binomial, but sometimes they have more than one group, more than one road, right? Could die, could recover, could go to hospital. So we're using multinomial. So anyway, and so for the process, we have we need to define a measurement model. So we using this negative binomial distribution. So our model like has some latent variables. So that's not observable, like a susceptible, exposed, infected, recover. But daily reported cases is somehow we assume it is the latent variable passed through a measurement model. This measurement model we assume is negative binomial for some reason, because in reality, if you observe like a daily reported cases, it's roughly following a Poisson process. And a Poisson process, we know Poisson process has one parameter, and a negative binomial has an additional parameter called over distribution. It's basically over dispersed Poisson. So that is what we use. And then another thing very important is when we try to find a model to describe a phenomena, we want our model to be as simple as possible. So we need to consider the model complexity. So we're using this information criterion as a rule to compare different models. So you could write a model has 5 parameters. You could write another model has 50 parameters, and the model has 50 parameters could do a much better job in fitting the data, right? So so the information criterion is a measurement of the trade-off between model complexity and the goodness of fitting. So basically, we want this information criterion to be as small as possible. That means your model as small as possible at the same time can do a good job. So basically, we're using those kind of epidemic models. So we divide population into different groups, as I said, right? And here, susceptible, exposed, infectious, recover. So we write into differential equations. And so this differential equation, most part is linear. It only has one part has a nonlinear beta times S times I here. Beta is transmission rate. Here, B is a birth rate, and mu is a death rate. So this is called a mass action function. It's from like a chemical experiment. So the idea is borrowed from that. It's called a mass action function. And this model, I'm using this model actually to model measles. Okay, and this model has a very nice feature. So here, here beta, if the beta is time dependent, let's assume like this annually, has a seasonal variable. So it's a periodic, and it will have a very nice propagation behavior, propagation tree. And if we changing the mean transmission rate, we can have a quite a nice, like here we have this biennial pattern. If we only observe the cases on, let's say, January 1st, every year we only observe the cases on January 1st, such that we have a Poincare map. It's something called, because when the beta has a periodic, your model is not has no stable equilibrium. It has a periodic. So we make a Poincare map by taking cases on a particular day every year. So we could observe those interesting phenomena. This here the blue, here the yellow show periodic 3, periodic 4. Anyway, so there are other models. For example, this one you could adding a structure, and here this model has 21 a structure. So every year we have one group, and among each group we have a SEIR. So totally we have 84 equations. This is a very famous model proposed by famous mathematician in 1984. And okay, we can fit in model to data. So here the dotted line, is observed measles cases in 1960, before the vaccine available in England. And the red curve is our model simulation. Our model simulation, if we tune in the parameter to the best. And this is our work, and with 4 equations. And the next figure shows the previous model has 84 equations. And I can convince you actually my fitting is better. Even though I have only 4 equations, here 84 equations. So I just want to give you an idea when you can develop a model and you want your model to be simple. Okay, COVID-19 here. Using this figure, I like to make nice figures. This figure showed in 58 locations, locations ordered according to their longitude. And using different colorful bars showed the different variant of SARS-CoV-2 dominate. It has more than 60% in the location among all the sample sequence. Okay, you can see that at the beginning, this black is the original strain, and this red showed alpha, and this is delta. Delta is quite highly transmissible, reached everywhere, and they omega B1, B2, and B5. Now we at B5. This showed actually this also showed suggesting that the transmission rate of a later strain must be higher than the transmission rate of a previous strain, such that it can replace. This is called replacement, right? A later one must have a higher transmission rate, and then we using, like I said, we develop these models. We cut population into different groups, and there is a transmission rate. There is a transition rate between different groups, and then we fit in this model to observed mortality, like a daily mortality in a country, and we implement the vaccination data, and then we fit in this model. Then we can rerun this model. At the same time, we remove the vaccination. Then we compare the outcome of these 2 schemes. We estimate how much lives saved by the vaccination. So here I showed in the United States, the red data is reported mortality, and the green is my model simulation. When everything we put it together using a simple model with vaccination coverage is this brown curve, and this blue is the transmission rate, estimated transmission rate, which I assume is a B-spline, is time dependent. Right, this green and the red are matching very well. And then I rerun this model, remove the vaccination, so I get this black curve. This black curve showed that the epidemic could be that high if your vaccination is not in place. So by comparing the green and the black, you get a number of lives saved. Right, that's the technique, and it sounds pretty easy, but it's not actually. Many teams try to estimate that. I would show you that our number are more reliable. For example, let's compare the estimate from a famous team, Empirical College. If you in this field, you will know that Empirical College team is the number one. They in January, if we record in January 23, they already estimate how many cases in Wuhan. At that time, when government reported 40, they estimated there is more than 4,000. So, but on this occasion, they estimate, for example, in the United States, they found that more than 1.7 million lives saved by vaccination in 2021 in the year, because our estimate is 666,000. Their case is threefold higher than us. But why I think our is more reasonable, because our estimate exactly matching the US CDC estimate. US CDC, they estimated this number. They have a much detailed data. They have a county level data. And this different county in the United States, thousands of them, and has different vaccination coverage, right? So they can compare different county. This county has a higher vaccination coverage. That county has a lower. There are some county for some reason, religion reason, has no vaccination somehow. So you can compare how much vaccine prevented cases. That should be a much reliable estimate. That number almost exactly matching ours. And the reason Empirical College is so high because their model has too many parameters. And I didn't show a plot of their model. If I show it, it's like 4 pages on the equations. So, and they update their transmission rate bi-weekly. This is quite different from ours. We basically update, we assume our transmission rate is a spline function. And we assume there is some number of degree of freedom. We basically assume on average every 2 months there is a nodes. So our number of degree of freedom in the transmission rate are much lower than Empirical College, and their model is too many parameters, and also the rate is quite high. For some other countries, also quite high. It's likely overestimate, over-exaggerate the vaccine effectiveness. The reason is, for example, Brazil. Before the vaccine available, there is a large outbreaks, and some study already argue that probably like more than 50% or even close to 70% of the population already infected. So that will compromise the effect of the vaccination. Basically, you infected, it's equivalent to or even better than vaccination, the effect, right? And so I'm not saying vaccine is not useful. Exactly opposite. I think the vaccination is saved a lot of lives, but we need to estimate that. We need to using simple, reliable mathematical models. So I summarize what I did is my team made a significant contribution at estimating key epidemiological parameters at the early stage of the pandemic, and the likelihood-based inference framework equipped with iterative filtering is a powerful tool in disease modeling. And also we, when we model, when we're using machine learning model to model complicated reality, we need to consider model complexity. We do not want your model too complicated, too many degree freedoms. And we estimate the 686,000 of lives saved by vaccination in US in the year 2021. Why I stopped at 2021? Because I needed to publish my paper. That's one reason. Another reason is in the end of the 2021, the Omicron emerged. The Omicron is quite different. Omicron can invade there is a breakthrough infection. Breakthrough infection means like if you vaccinated, also the Omicron still can infect you. That's a breakthrough infection. And also there is a reinfection. If you previously got infected by Delta, you still can be infected by Omicron, like with some probability. So Omicron really changing the story of, for example, the herd immunity. We didn't talk about herd immunity that much because there is a reinfection, right? The previous, like measles, you in your life, you only get it once. Okay, there is herd, but in terms of lives, it's I think we probably reach some kind of a herd immunity now. In terms of mortality, not infection. Okay, and okay, thank you.
Okay, good timing. We are exactly following our schedule. So next, let's start our Q&A session. So we can invite our three speakers to sit here. In addition, we also have two research assistant professors from ABCT. One is online, and the other is on-site. Okay. So in this Q&A session, we invite questions from the audience, and the speaker can also ask each other. So any questions from the audience? So there is already one question in chat. So who is willing to take this question?
This one is no, it's for technical questions.
Okay, so any questions from the audience, on-site and online? Any question from audience?
Okay.
Okay. Okay. We have.
Oh
no. Okay.
Maybe I have the first question.
Okay,
So it's very well. I'm not very good at math. So first of all, but I did hear an important message from Daihai's talk is that. You just said that the COVID is about to the end in terms of the mortality, not in terms of the infectious, right? Does that mean that we will keep having new cases, for a very prolonged time, but the mortality would not increase, not much?
Yes, I would think so. If there is no new variant with a higher mortality rate emerge, condition on that.
And the other question is that while I was looking for the clinical trials of the current vaccinations, I noticed that in the phase 4 of many like COVID vaccines, they start to mix, like kind of use more than one kind of vaccination. For instance, they use the COVID-19 vaccine together with the EV71, which is an enterovirus, which is also an RNA virus that is very difficult to kill. And the other one use COVID-19 virus, EV virus, EV71, and there is another one, which I can't remember the name now. So would that become a trend that maybe the multivalent of the vaccinations will become a trend? I don't know if your research covered that part.
I don't know. That's not my expertise.
Thank you.
Okay. Any question from on-site audience. I have one question for Professor Yan. Professor, you show your electrochemical transistor has very high selectivity from the virus. So for COVID-19 virus, we have alpha, beta, Omicron. And even for Omicron, it has a BA1, BA2, and BA5. So can your sensor selectively detect this different types?
Well, here we just report the antibody detection. So we just demonstrate the detection of antibody for all of the COVID infection cases. Okay. So if we want to detect some specific variable of this COVID, we should choose some more suitable antibody. But we just use a very general one, so we cannot separate different variables for the antibody.
So for the electrochemical transistor, can we repeatedly use it for many times?
No, it's
just
disposable device. We can use it one time. It's just like the fast test some other RATs.
Okay.
So just use one time. After the reaction, you cannot use it again.
If it's only one time, how about its cost? Because we have to use some electronic circuit to detect the signal.
Yeah, cost is very low. It's comparable to the existing technique. Because we use a disposable device that meter is can be used for many times. We just test it and throw it away and replace a new one. As for the test strip, it's low cost. It's not just we just fabricate the device on a piece of plastic. So it's low cost.
Okay. I have another question for Dr. He. So recently, Hukong government the control measure is linked up. So according to your model, do you have any expectation for the COVID-19 trend in Hukong?
I think that infection probably would at a low level, but most importantly, mortality unlikely go very high. So that's the reason for the government to lift those control measures. I would expect, as I said, probably the transmission could lasting for a longer time, but mortality at an acceptable level somehow.
So according to your model prediction, so when can we return to normal life?
How you define? Depends how you define normal life. I quite optimistic. Put it this way, even though we see many variants, alpha, beta, delta, omicron, but the previous variant, the immunity evasion ability not high. So basically you got once you protected from the second variant. Omicron is quite different. Omicron can, you get infected, Omicron can reinfect you or breakthrough infection, vaccine breakthrough infection. But Omicron is only every 2 years, only after 2 years we see Omicron. So I wouldn't see another Omicron very quickly emerge. So in general, I would think that it's the peak is already passed, I think. But for example, for influenza, every 2 years, basically we see a new variant. So that's why the WHO would need to update their vaccination annually. So probably COVID will enter that phase. So we need to update our vaccine. Probably annually, we need a vaccine annually for those high risk group. Okay. I have some question for President. It's a very so you showed a figure with time and the positive rate. That is for one person, right?
Yeah.
So for one person, so if the curve eventually would decrease.
Right.
So that's similar to Elisa, right? That but you know, because I also see some data from different platforms. There is one platform from Abato. I'm not sure you must heard of this Abato, and their drop very quick. So that means their sensitivity dropped like after 1 month or 2 months, you already negative, zero negative. But we want using this, we want to show that people like we want to see someone whether infected in the past, right? So how your platform compared to their? It will decreasing or it will constant?
So, well, the figure showing my PPT is from some paper, not my data, but the figure just shows. So we just want to show that antibody in human body will increase after we get infection, and then it will saturate and then slowly decrease after several months. It will decrease to very, very low level, and then probably we may need another vaccine. So but for the figure, it depends whether you will have the linear plots or log plot. If you have a lot of plot, you may have shear very slowly.
Yeah, but if the equipment is very sensitive, so I can tell. So I can tell, for example, someone got infected half a year ago. Probably it's irrelevant. This person become acceptable anyway. But can we tell if someone half a year ago, can we tell this person infected?
For all device, we can detect several of these detection regions about 6-7 order of magnitude. Very broad.
Very broad in terms of time.
So in terms of the concentration.
Concentration.
Several order of magnitude can be differentiated.
Okay, I see.
Not linear. So for example, you change 10 to 1. Very we may vary to 10 to minus 14. So we can have we can monitor the change in very broad range.
Yeah. Because I have this question because there are a lot of debate. There are a lot of equipment to testing serological antibody, and some like this Elisa, there are some platform can give a very sensitive result, and some other platform like Abato, there's one of them give a very quick drop. It can give you initially, it can give you very high sensitivity, but it drops very quickly. So after
the problem is if the sensitivity is enough, it is not a matter of the instrument. Okay? It depends on the human body, the real concentration, right?
Yeah.
But if you plot out the data in log or in linear, you may have different shape. But the data should be accurate.
But because those, my understanding, I'm not expert. My understanding is different platform has a different threshold, cutting threshold.
Yes.
So if you're setting very low, you can say, okay, this person is positive.
Some instrument will not give you the actual concentration. For example, in the body fluid, like in saliva, what is the concentration? Probably they can just give you whether it's positive or negative.
Yeah.
So you will not get the actual data from the like a PCR. Probably the PCR just tell you, oh, it's a positive or negative. But
it also give you CT value.
Yeah,
that is also important.
But it is not a concentration. It's not an information concentration.
With the standard curve, yes, we can convert it to the actual copy number. Yes.
Yeah, somehow CT value.
Okay. So depending on the technique we use.
Yeah.
think that's also part of the reason why some of the rapid tests are not cannot be used as IVD, because if you don't have that clear relationship being established, then it can use for like a qualitative result interpretation. Yeah.
I have a suggestion. I'm very naive. Maybe your equipment, for example, we can using like a testing your result, and there is APP tells me you likely be infected in what time interval. Is that possible? Like for example, 2 months ago or 3 months ago, right? If you have this curve, basically somehow.
Right. Yeah.
That's a very ideal situation. I would say, like, based on I don't have the data for COVID-19, but I did see the data from SARS-CoV. So with sufficient N numbers, subject N numbers, yes, they have plot and population like what you said, the titer of the antibody drop, increase, and then drop after a certain period of time. But you rely heavily on the immune system of each individual. So the pool has to be big enough so that it's possible to.
So for example, this equipment can tell me, because I know there's it's probably an individual issue.
Yes.
But if there is a APP can tell me when I got infected and when I might need a second dose or third dose, that will be that could be a selling point of your APP, right?
Yes.
And now the topic becomes less important. No one will care about the
You might need still.
I don't think so. Influenza has been influenza has been in human history for 100 years, but still we have annual vaccination campaign, right?
So for scientific purpose.
Right. So I think COVID-19 maybe become another one, like the annual one, but it won't be a mandatory in the future. It will be provided to those who are more immunocompromised or like the elderly in the future. Yeah, like seasonal flu.
Also you using the term herd immunity. So I want to comment on that, because there is a lot in this COVID-19 pandemic. There are a lot of debate. At the beginning, people say, the UK government, they say, okay, we can flatten the curve, we can reach herd immunity. But when gradually, when Alpha, Delta come, the transmission rate increase, it makes it very difficult, because the Delta variant has a 0.5. That means like you need a vaccination, you need infected like more than 80%. That is some 80%, 90% coverage vaccination. That is very for if the vaccine is 100% effective, but the vaccine is not 100% effective, it makes it very difficult. And also there's a lot of debate. There's reinfection. If you allow reinfection, basically means your herd immunity is failed. Actually, I'm on the side of I'm a herd immunity believer. I believe herd immunity. We still have this herd immunity concept, but it's probably more on the severe cases and the mortality. You cannot die twice, right? So that's a kind of a herd. It's basically for some countries, for example, some low-income countries, Peru, they have a 0.6% of the population died. That is quite significant, and it seems like in the past.
But that is the case before the Omicron, right?
Yes, the Omicron become very mild, because 0.6% of the population died. That is a quite big number. So that makes everyone probably not the poll for the mortality is run out. So Omicron didn't cause a lot of deaths.
Okay. I have a question from Amber. So our PolyU have a facility from the test COVID-19.
Yes.
So what are the advantage of our testing with service
Over CTC? Well, it's convenient, basically it's on campus. And for our colleagues, like, yeah, we have the collection booth on campus, right? So if you happen to have the CTC next to your home, then of course, I guess there's no difference. But for colleagues who may have to spend extra time to go to a CTC to have the service, then you're welcome to use our on-campus one, because since it's also one of the list in the government recognized COVID-19 testing centers. At the same time, if the colleagues or students have some activities on behalf of the university, such as business trip or service learnings, you can also use it to issue the travel certificate, which is free. Yeah. Although we provide service for external parties, but they have to pay. Yeah. And there is a major difference between this one and the CTC. More on the logistics side is that for people who want to have their compulsory test, for instance, they go to a CTC, they don't need to pay because that fee is subsidized by the government. While in our case, the fee is subsidized by PolyU. That's why we don't provide free service for external user. Okay.
Dr. He, did you use your model to analyze the case in North Korea?
No.
Do they have data? Do they have data?
We did have some data, but
I don't know. For some reason, I didn't. I focusing on those countries reported a lot of cases.
yeah,
Actually, I did a lot
because
of.
this country they didn't get an emergency.
Yeah, it's not transparent, so you don't know the data. There's no particular reason why I would pair that there. So I just no.
Yeah, I believe transparency of the data is an important factor to ensure that the model is correct, right? It's true. Yeah.
For some countries like India, the underreporting is very high. So that is actually, there are a lot of work published in Nature Science discussed. Okay, but anyway, they have data. They have right. You can play with. They have data. They have access tests. So you can see likely how many people die.
Okay.
I have a question actually for you too. When you're dealing with this environment, do you need some kind of certificate? I think it's quite risky, right? Some kind of.
No, we didn't do the clinical trial. We just use biomolecules instead.
But still, you
No virus.
no virus.
No.
For us, we did. That's why we need to. That's why we. Why it is important to obtain that HOCUS, because it's accreditation for medical laboratory who can handle those clinical samples, and that which is also why we need the MLT, the medical laboratory scientists in the lab. They are qualified to do the work.
So can you do it in PolyU, you mean?
Yes, it's in PolyU in there. Yes.
So test the virus?
Yes.
Okay.
But we mainly deal with, well, we don't culture the virus. We don't culture the SARS-CoV-2 because it requires a BSL-3 lab. The one we have is BSL-2. So the samples we bring in may contain the live virus. So what we do is we lyse the samples, we lyse the cells and extract the RNA for detections. But still there is a risk being infected from these samples. Yes.
Okay, any question from audience? Okay, please.
Professor Yan, your device is very fascinating. Yeah. To my knowledge, I think the PI form of the antibody will be ranged from pH 8 to 9. So which means that some of the antibody will have a higher positive charge density under the same environment. Would this lead to the overestimation or underestimation of the signal you have when detecting the antibody in the blood or in any sample?
So for measurement is based on the detection of this charge, okay, the electrolyte. So we find the optimal condition, optimal pH value is about 5. And for this antibody, I remember the isoelectric point is 8.2 like that. Okay. So in this case, we can have some positive charge on the surface and we can detect it. So all of the data we should can be, so you know, the concentration can be evaluated based on the calibration. So after we have the calibration, should have according to the signal, you can calculate the concentration.
I have a naive question. So you can, it's antibodies, you can distinguish between it's an infection or it's vaccine induced.
No.
No, you cannot distinguish that.
We just test a very simple antibody, IgG, but there are
So
many.
this could be vaccinated. Oh,
Yeah. So IgG, you know, is after you get infection or vaccine, you may have a very high level antibody.
yeah, I know.
There are many types of antibody like IgA and
IgM.
or many, but we just demonstrated the application IgG is most commonly found antibody. But we also can detect many other type of antibody. So based on the same principle.
Yeah, it's quite amazing. You do not need blood. That to me, that's an advantage.
Well, but for RIT, we'll take the
Yeah,
live.
but for other equipment, for serological, they need blood.
Never for antibody, we need blood.
But
Yeah.
you also antibody.
Yeah. But because our sensitivity is high,
Yeah.
so we don't
Enough
need
blood,
the
yeah.
antibody. We don't need the blood. Yeah, blood.
Okay, any questions from online audience? If no question, it's just follow our schedule. So let's set our 3 speaker guide and set all the audience and set our supporting staff. They prepare long haul for this seminar series. Okay, so our faculty actually also will continue to organize this kind of seminar series. Next month we will have another one, and we will announce the email, and we hope to more students can come to join this seminar. So that's all for today's seminar. Let's section get the 3 speakers.